Hi, my name is Stuart Ozer, and this is Lab 3. So the purpose of this lab is to learn how to determine the magnetic field from a bar magnet and to simulate this process in GlowScript. The fundamental principles and models used here are the bias-Savart law, magnetic fields in general, magnetic dipoles, and distance dependence. The system here was the bar magnet, and the surroundings here was Earth and other magnets, etc. The necessary physics principles we used was the bias-Savart law, as you can see there. The magnetic dipoles was the formula given to us in the PDF, you can see that there. And distance dependence is kr to the n, but then the linearization of the x component of that is, as you can see, ln of the x component of that equals ln of k plus n times ln of r, where n is the slope of that line, r is the distance, and k is some combination of constants, including the magnetic moment. There are very many sources of error here, but the big two ones are general human error. I'm not perfect. I did some things wrong. And the external magnetic fields, I did this in a room with other devices, which meant there were definitely other magnetic fields that could have interfered and possibly did interfere, causing the difference in data that we'll see later. I calculated the moment to be 0.37642 with a slope of negative 2.864. And then we can see the computer results there, and we'll get to the comparison in just a minute. So initial conditions, the bar magnet is stationary and the phone is stationary. And then for the experiment, we determined the location of the magnetometer on the phone by lining up the phone to the axis. Then the location was found to be mid-right of the phone. And then we measured B at multiple R's, and those R's were the locations where the BX value was 20, 70, 120, 170, and 220. And then we recorded that BX along with the R onto the Excel sheet. And then Excel calculated N from the formula B bar equals KR to the N. And then we determined the moment of the bar magnet from the formula mu0 to mu over 4 pi r cubed, and we set that equal to the B bar, and then we solved for mu. So, looking at our data, those were all the average. In the blue, you can see the average locations for each average BX value, and then that gave us the equation with the slope of negative 2.684x, that's your n times x, minus 16.402, minus 16.402 being ln of k. And then we got a B net value of 0.000166. We'll get to that in a minute. The code here, going through it quickly, first we create a function after we set our initial value of 0.37642 to be that's the magnet moment. We create a function, the stuff I did. So we find the magnitude of R to get R mag. We take the hat of R, so R over R mag, and then we take the cube of R mag, and then we find out what mu dot R hat is, and then we calculate B using the formula we mentioned earlier from the PDF, and then we return that function. We set up a few observation axes, each that are on a distance on one of the axes away. And then for R of axis, we just set the R axis to be the observation axis, and then we apply our function to calculate B, and then we create a vector arrow with those properties, and we do that for each of the on-axis and each of the off-axis. And so then we do a 45-degree calculation, and then we will get a value for that of the magnitude to be 0.000005, which is greatly different from the value we got in the data, and that's because of all those other magnets in my room that I was doing it in affecting the results of the lab. And you can see the B values here were also very different, and like I said, that's due to the error created by the other magnets around me in the lab. So, moving on to our questions. What if you hadn't orientated your experiment to compensate for magnetic north and had instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field? How would your results have changed? Well, Earth's magnetic field would interfere with measurements of the bar magnet's field even more and would be canceled incorrectly, so the results would be skewed. This is actually likely what happened with my data, along with other magnets interfering as well. And then what if you were to stick two identical magnets together end to end and run the experiment again? How would you expect your measurements to differ? Well, the magnetic field magnitude would double in size, and the direction would remain the same because the poles would still be north where north was and south where south was. And the magnetic moment would be doubled because you have two magnetic moments added together. And so it would have the same direction, but they would double in size. And that is it.